3-minute video with Daniel. Today we'll now solve question 1J from MAT 2013. This was suggested by Stewart Poynter, but I uploaded it once, but for some reason it just disappeared. Anyway, today's episode is a 90 of its kind. What is 90? One very useful fact about 90 is that it's a product number. It's a product of a number and 1 plus that number. Really interesting when you think about it. And half a product number, when you divide it by 2, it is a triangular number. 45, in this case, is a nice triangular number. And every product number, when divided by 2, reduces to a triangular number. Now, this MAT question asks us to find the area of 0 to n on this absurd looking graph. What is this absurd looking graph? It's basically to find the integer less than or equal to x. So let me draw a small snippet of the graph. Let's start with 1, and then 2, and then 3, and then 4. You see? 1, then we have 2, and then we have 3. Now where do these lines stop? They stop at log 2, log 2, 3. Now how do you calculate the area of a rectangle? So it's 1 times 1 plus log 2, 3 minus 1 times 2 plus log 2, 4 minus log 2, 3. Keep in mind that log 2, 4 is just another way of writing 2, and then times 3 plus, and so on until log 2 to the power of 2n minus log 2 to the power of 2n minus 1, and then we multiply it by, well, I know what you're expecting. Do you see here? Times n. Now, if you do it this way, then you will now have 1 plus n to the power times 2 to the power of n minus 1 minus log 2, 3 minus log 2, 4 minus dot minus log 2 to the power of n minus 1. Actually, the minus 1 is supposed to be here. Minus log 2 to the power of n. Understand? Now you have the 1s and the 1 cancel out. So that means that n times 2 to the power of n minus the log of 2 to the power of what will be called 2 to the power of n factorial. An interesting thing, right? Well, besides the factorials, it goes in the log sign so you don't get confused. But anyway, thanks for this. And by the way, this absurd looking square brackets are actually called the floor function in recreational mathematics, discrete mathematics, number theory, and so on. And I'll leave it to you to explain other ridiculous graphs. I know, we all like ridiculous graphs. We all love spice in our life. That's why we love ridiculous graphs. Isn't that nice? Anyway, I'll leave it to you on these explorations. Goodbye!